Hey everybody, this is a AP Physics C question from 1995. It's got a lot of good conservation of momentum and a little bit of horizontal projectile problems thrown in there. So let's go ahead and look at this. We got this 0.5 kilogram block sliding along at 26 meters per second, and it's going to hit this 5 kilogram ball right on the edge of the table there. There's no friction on the tabletop that we have to worry about. And right here they say this figure below shows the graph of the force exerted on the ball by the cube as a function of time. So it's a force versus time graph. So right away we should be thinking here about the area equaling the impulse there. One thing to notice here is this is time times 10 to the negative 3 seconds, and this one says force times 10 to the 3 seconds. So if you noticed one of these but not the other one, you might make a mistake. If you forget both of them, it turns out to be okay because this one cancels out that one. All right, so our very first question here is determine the total impulse given to the ball. Well, as we just said, what we are going to try to find there is the area then is equal to the impulse. So let's come back to this graph here and look at this one. You can see here that I've got a triangle right here. I'm going to find the area of that triangle, but I actually have the exact same triangle right here. So rather than doing 1/2 base times height, and then multiplying that by 2 to get the two triangles, and basically, if I take that other triangle, just stack it here, I've got a cube, right? So this cube is, not cube, rectangle. It is 4 by 2, so the area of this one is 8 there. So that is the impulse. And then inside of here, I've got this little rectangular area, and this one is 2 by 2, so the area of that one is 4. And that means when we come back over to here, we have 8 plus 4 for a total impulse of 12 Newton seconds there. Okay, next thing they say is determine the horizontal velocity of the ball immediately after the collision. So now what we need to say is that that impulse is also equal to change in momentum, which is equal to mass times change in velocity. That is how we change the momentum. So now we can plug in here and start to solve for these. We already have the impulse, so we already have the change in momentum. So the change in momentum is 12 kilogram meters per second. The mass they told us for this ball was 5 kilograms. So we can solve for that change in velocity. And that change in velocity, 12 divided by 5, is 2.4 meters per second. Now, careful, this is the change in velocity, not necessarily the final velocity. But in this particular case, since we started at 0, it is both the change and the final velocity there. So 2.4 meters per second there. All right, next up, part C. It says, determine the following for the cube immediately after the collision. Its speed. All right, this is a conservation of momentum problem. So we know the momentum of the system beforehand is equal to the momentum of the system afterwards. So now, let's think about this particular situation. That means we had the momentum of the cube before the collision has got to be equal to the momentum of the ball after the collision plus the momentum of the cube after the collision. So now let's start to expand these. And remember, we already found the momentum of the ball. The change in momentum was 12. It went from 0 to 12, so we have that. All right, now, next part here, let's start to fill in for this. The momentum of the cube before will be the mass of the cube times the velocity of the cube before. The momentum of the ball afterwards, we've already found, that's 12. And then the momentum of the cube afterwards will be the mass of the cube times the velocity of the cube afterwards. And that is what we're looking for, is the velocity of the cube afterwards. So now let's start to plug in for all of this that we know. We know the mass of the cube, if we look back on here, was 0.5. So 0.5 kilograms times the velocity of the cube. They told us on the front page that that was 26. That is equal to 12 here plus, again, the mass of the cube is 0.5 times the velocity of the cube afterwards. 26 times 0.5 here will give us 13 is equal to 12 plus 0.5 times the velocity of the cube afterwards. Subtract the 12 from each side, and we will get there 1 is equal to 0.5 times the velocity of the cube. So divide each side by 0.5, and we will get the velocity of the cube afterwards is 2 meters per second. Okay, now it says what's its direction of travel, right or left? Well, it's right because this is positive there. Okay, next up, part D here. It says determine the kinetic energy dissipated during the collision. So what we're going to have to do is to find the kinetic energy of the cube before the collision. So 1/2 times the mass of the cube times the velocity of the cube before the collision. That is 1/2. The mass of the cube is 0.5, and the velocity of the cube before the collision was 26. Don't forget to square it. So if you do all that math, you'll get 169 joules was the energy before the collision. Now, let's find two kinetic energies, the kinetic energy of the cube afterwards and the kinetic energy of the ball afterwards. So to do that for the cube afterwards is 1/2. Mass of the cube again is 0.5. We've already solved that afterwards the cube will be going 2 meters per second. Don't forget to square it. And then kinetic energy of the ball, 1/2. The mass of the ball is 5 kilograms, and we've already solved for its velocity afterwards. That's 2.4 squared. So do all of that algebra there, punch it into your calculator. For this, you will get 1 joule. That's a joule, not a 5 there. So 1 joule plus, for all of this, you will get 14.4 joules, which means that we have a total here of 15.4 joules afterwards. Now, one final step here to get the answer. They said the energy dissipated. So how much energy did we lose? Well, we had 169 joules. We lost 15.4 joules. So you subtract those two, and you get 153.6 joules was lost during the collision, making this an inelastic collision. So remember, even though they actually bounce there, just because they bounce, that doesn't make it elastic. You have to look at what happens to the energy in order to see if it's elastic. All right, one more part here, and they kind of switch it up, do a little bit of a horizontal projectile review here. It says determine the distance between the 2 points of impact when the objects hit the floor. So let's bring this picture back here for a second, right? They were on this tabletop, so everything so far could have just been on a flat surface. So the ball gets hit and knocked off, and it goes down like this, and the cube continues to go forward, we know, so it's also going to become a horizontal projectile here. All right, so we're trying to find their distances. So when you do a horizontal projectile problem like this, you got to start with the third equation. The vertical distance they move is equal to the initial y velocity times time plus 1/2 times the y acceleration, which is g, times time squared. There is no initial y velocity for a horizontal projectile. So when we go to solve for this time, this is an equation you should have memorized. It's square root of 2 times the height over g. Let's plug in for this. Be careful here. Go back to this picture here. The height that we have on this one is 1.2 meters. So it's 1.2 meters high. So 2 times 1.2 meters over 10, square root of all of that, and you will get 0.49 seconds to hit the ground. So that's how long we have to fall. Now, next up, let's figure out where they land. Generically, when we're trying to find how far a horizontal projectile goes horizontally, we're going to use the same third equation, but in the horizontal form. So delta x equals, but this time there's no acceleration, so this part's gone. So we simply have our x velocity times time. Now, here's what makes this one a little bit weird. They want to know the difference in the distance that they land. So you can plug this in for each one and solve how far the ball goes and how far the cube goes, and then subtract those two. Or if you want to look at it this way, one of them here is going 2.4 to the side. 2.4 meters per second. The other one is going 2 meters per second. So that difference in velocity there is simply 0.4 meters per second. That relative difference is all that matters. So we can actually plug that in for our velocity here and solve it that way. So this difference in distance here will be our velocity, a difference of 0.4 meters per second. And how long do we have to have that difference? 0.49 seconds before we hit the ground. So when you multiply those two out, you get 0.196 meters.